Hi, my name is Cecilia Testart, and in this video, I present you our work to filter or not to filter, measuring the benefit of registering in the RPKI today. It is well known that BGP, the inter-domain routing protocol of the Internet, is notoriously insecure. The RPKI is a relatively new mechanism to increase BGP security. In this work, we empirically study how widely the RPKI mechanisms are deployed in the Internet and to what extent the RPKI protects networks against harms that arise from misconfiguration and hijacks. I'll start by giving a brief overview of BGP and the RPKI before diving into the research. The Border Gateway Protocol, or BGP, is a protocol used by large networks in the Internet to exchange routing information. Here, for example, we have a simple Internet topology with a few autonomous systems, ASs. An AS3 wants to let the rest of the Internet know the IP address block of its network. So it sends a BGP update to its neighbor ASC, who then forwards this information to its own neighbors. This is basically how BGP works. The problem comes when the network sends incorrect information in BGP. For example, here this network sends a BGP announcement that reaches ASD, who has no mechanism to verify the validity of either announcements and might choose the wrong one and then propagate wrong announcements to the network. And again, none of those ASs can verify the BGP announcements that they get. This is what happened in the case of a hijack, because BGP does not include a mechanism for root validation. The RPKI is a building block to improve this. The Research Public Key Infrastructure, or RPKI, is one of the most recent attempts to increase BGP security by providing a trustworthy and cryptographically verifiable database that maps prefixes to the AS number that is authorized to originate this prefix in BGP. Regional Internet registries serve as trust anchors, allowing ISPs to register and cryptographically sign Root Origin Authorization, or ROAS. A Root Origin Authorization asserts a prefix, such in this example the 18.0.0.0/16, and the autonomous system number, in this example AS3, that is allowed to originate it in BGP. RIRs have databases of these root origin authorizations, and then networks can use this information to validate announcements in BGP, and I'll explain more of that in a second. Currently, about 20% of IP prefixes seen in BGP are covered by valid ROAS. And recent research has shown that now RPKI records are of good quality, with very few of them having errors of misconfiguration. But the benefit networks get from registering the prefix on the RPKI depends on RPKI enforcement. And now I'll explain what I mean by that. Let's come back to our example. Let's suppose that ASD in this picture is enforcing RPKI in its RPKI-enabled router. This means that it checks incoming root announcements against prefix-origin information of ROAS. And following the example, that includes the root origin authorization of the /16 prefix originated by AS3. When an ASD receives the BGP update from AS666, it is discarded as it is invalid with respect to RPKI records. ASD therefore does not propagate the wrong information. When it receives the update with AS3 as an origin, it validates the information, and as it is correct, it installs that route in its routing table and then forwards traffic to that origin. It also then propagates the right announcements to its neighbors. Recently, networks such as AT&T have announced that they started enforcing the RPKI, but there is mostly anecdotal evidence of RPKI enforcement and its impact on registered prefixes. In this work, we measure the level of RPKI enforcement and how it impacts prefix reachability. Our research goal is to understand to what degree registration in the RPKI protects our network from illicit announcement of their prefixes, such as the case shown in the example. For that, we start by measuring RPKI enforcement over time for the past few years by counting how many networks filter invalid RPKI records. And I will use RPKI enforcement and RPKI filtering interchangeably. Then we study how much RPKI registration protects networks by studying the visibility of prefix-origin pairs, how this pair spreads through the network depending on their RPKI status, and then even more specifically, the visibility in the case of conflicts, such as what happened in the case of hijack, like the previous example. I'll now present you the datasets we use for our analysis. Our RPKI data comes from daily snapshots of validated root origin authorizations provided by RIPE NCC RPKI validators. These give us a list of prefix-origin pairs that are properly registered in the RPKI. RIPE makes this list publicly available in their webpage. We extend that dataset with historical data made available in the study of Chang et al. Presented at IMC last year. We match this data with two BGP datasets with real data collected through BGP collectors from RightBreeze and RouteView. In total, there are over 1,000 AESs that peer with collectors from this infrastructure and send them their BGP data. From this, we first build a longitudinal dataset composed of all RIP dumps from these collectors on the first day of the month, starting in April 2017 until the end of January 2020. Second, we build a fine-grained BGP dataset by processing all BGP updates from this infrastructure for the month of September 2019 to extract prefix-origin pairs and the AESs that have them in the routing table over time. With these datasets in hand, our first step is to detect RPKI filtering. Our method to detect RPKI filtering consists in two steps, and I'll use the graph on the side to illustrate it. In this graph, each dot represents a feeder AES, that is, an AES that peers with the collector infrastructure, and its position depends on the prefix-origin pairs it sends to collector. The total number of prefix-origin pair a feeder AES sends to the collector is on the y-axis. The larger the number, the more BGP information AES is sent to collector. And on the x-axis is the number of prefix-origin pairs sent by an AES that are invalid according to the same-day RPKI record. So the larger the number, the more RPKI invalid pairs forwarded by AESs. It turns out that not all feeder AESs share the full routing table with the collector infrastructure. To detect filtering, we first select full feeder AESs. That is, AESs that send the equivalent of a full routing table to collector. We define our threshold as the 75% of the maximum number of prefix-origin pairs sent by a feeder AES. Here in the graph, you can see the set of full feeder AESs in this example. Then, for these full feeder AESs, we select the one with a low number of RPKI invalid prefix-origin. Here in the graph, you can see the threshold. AESs on the top left corner of the graph are the ones we infer are filtering invalid BGP announcement with respect to RPKI records. With these two steps, we can detect RPKI filtering with high certainty, as the difference in RPKI invalid counts among full feeders AESs is statistically significant. There are about 300 full feeder AESs in IPv4 and 250 in IPv6. Using this methodology, we track RPKI filtering over time and find that RPKI enforcement is starting to gain traction. At the beginning of our measurement window in 2017, less than 2% networks we measure are enforcing RPKI. It slowly increases during 2018 and accelerates its growth in 2019, especially between April and August 2019. It more than doubles during that period. In our last measurement from 2020, about 10% of network we measure enforce RPKI. Now, let's see how well this approach works when comparing with ground truth using public announcements of RPKI enforcement or filtering. We find public announcement of RPKI filtering for 5 AESs that share the full routing table with collectors. This graph shows the count of invalid IPv4 prefix-origin pairs they forward to collectors over time. The higher the count, the more invalid information they forward. At the beginning of the graph, in early 2019, we see that all AESs forward about 5,000 invalid prefix-origin pairs to collector, and then at some point they go down closer to 0. Now, these vertical dashed lines correspond to the date of the public announcement of RPKI filtering. We can see that our method detects when RPKI filtering was finally implemented. The orange dotted line correspond to the date Telia, AES 1299, announced the beginning of their deployment of RPKI filtering. Indeed, things are more complicated than just jumping down to zero. For instance, Telia has been slowly deploying RPKI filtering since its announcement in September 2019. And as we can see, the number of RPKI invalid pairs it forwards to collector is slowly going down more than having a one-time decrease. What we can also see in this graph is that none of these AESs appears to be filtering all RPKI invalid announcements. There are always a few dozens or hundred left, and there can be large periods where filtering disappears. We look into this, and on top of coordination delays between databases, we find three main reasons for partial filtering. First, not all filter AES consider ROAS for all 5 RIRs, the trust anchors, to verify BGP announcements. Indeed, 25% of the AESs that are enforcing RPKI do not consider ROAS from ERIN. ERIN is one of the 5 RIRs, the RIR of North America. This is because ERIN TA is not included by default in RPKI validator software, because ERIN requires the approval of a legal agreement before allowing to manually include it. Many network providers either do not go through the trouble of doing that or do not agree with ERIN legal terms. Second, RPKI filtering depends on AES relationships. Many AESs that are filtering do not drop RPKI invalid announcements from their customers, or they give them a grace period to get this announcement fixed. That is the policy of AT&T, for instance. Other AESs decide to only filter RPKI invalids they receive through an IXP or from transit providers, but not from other relationships. So filtering really depends on AES relationships. And third, some network has reported operational issues during the deployment of RPKI filtering. Some of these are linked to the RPKI validator software, making them use only a subset of all ROAS available, and other issues are linked to router software and bugs in the implementation of BGP announcement validation using RPKI data, making AESs implement filtering on a subset of their border routers. I'll stress that we're able to measure this difference in filtering because of the comprehensive information we get from AES sharing their full routing table with the collector infrastructure. But although AESs may have different levels of filtering, there is definitely a significant portion of them enforcing RPKI. With this encouraging perspective, we went and studied in detail the impact of RPKI filtering in September 2019. We want to assess how much the RPKI reduces the reachability of invalid prefixes with respect to RPKI records, that is, the prefixes registered in the RPKI. For that, we built a fine-grained dataset for the months of September 2019 by processing old updates from the BGP collector infrastructure to extract Prefix-origin announcements over time and build Prefix-origin timeline corresponding to the time a given Prefix-origin is seen in our BGP data. We then paired this timeline with daily RPKI validation status. This table provides a summary of the RPKI coverage of Prefix-origin timelines that we built. A bit less than 20% of prefixes seen in BGP are covered by RPKI records, and most of them have a valid status, except a few thousands that are invalid, meaning that for those prefix-origin pairs, the prefix is covered by an RPKI record, but the origin or the prefix length does not match the RPKI record. We found about 1% of prefixes in BGP that are RPKI invalid in our measurement window. As you can see, results for IPv4 and IPv6 are fairly similar. In the rest of the presentation, I'll show you the results of our study for IPv4. You can find IPv6 results in our paper. Now let's see how prefix-origin pairs spread through the network depending on their RPKI status. In this CDF, we see for different RPKI status the distribution of visibility among prefix-origin pairs. And by visibility, I mean the percent of AESs from all the AESs we have data from that has a given prefix-origin in the routing table. The visibility percent is on the x-axis and the fraction of prefix-origin pairs on the y-axis. RPKI invalid pairs visibility distribution are represented by the red and orange line, while RPKI unknown and invalid visibility distribution are in green and blue respectively. We can see that RPKI and valid prefix origin indeed have lower visibility than RPKI valid or unknown. On the bottom left corner of the graph are very localized prefix origin pairs, and we can see that there's a significant share of RPKI invalid pairs that have very low visibility. Indeed, about 20% of RPKI invalids are seen by less than 10% of active pairs. More interesting though, on the top right corner of the graph are the high visibility pairs, and we can see that RPKI invalid prefix origin never reach the highest levels of visibility. This is a direct consequence of networks dropping RPKI invalid announcements. The difference is between 10 to 15% points in visibility. We then go and study more in detail prefix visibility in the case of conflicting announcement, which is what we'd expect to see in the case of an attack or of a hijack. First, we will look at the case of a multiple origin AES conflict, which is what happened in the case of a prefix hijack. Going back to our earlier example of a BGP network, that was a MOAS conflict because the same prefix was originated by two AESs at the same time. AESs that receive both updates need to choose one, and without using RPKI validation, they can choose the wrong announcement. But when an AES implements RPKI filtering, such as in this example ASD with its RPKI-enabled router, it discards the BGP message with the wrong origin for the prefix and forwards the proper one. So, MOAS conflicts are candidate events of prefix hijack, and to study the effect of registering prefix in the RPKIs in such cases, we study the visibility in the case of MOAS. For this, we first select from a dataset prefixes covered by an RPKI record that are being announced by two different origin AESs, making one announcement RPKI valid and the other RPKI invalid. In this graph, you can see the normalized count of prefix origin for different levels of visibility by RPKI status. RPKI invalids are in orange and RPKI valid are in blue. We see that RPKI valid really dominate in terms of visibility. About 70% of them have visibility over 70%, whereas about 60% of RPKI invalid have visibility below 30%. Now we want to compare these results with what happens if a network did not register its prefixes in the RPKI and a MOAS conflict appear, potentially from a prefix hijack. For this, we compare this result with the visibility distribution of pairs of MOAS prefixes that are not registered in the RPKI. Of course, then the challenge is how to attribute legitimacy between two pairs of a MOAS conflict. As a proxy, we use the length of time a prefix origin has been announced during September 2019. If a prefix is not registered in the RPKI, the status of its RPKI validation is unknown, so we compare the results of pairs of one RPKI valid and one RPKI invalid prefix with pairs that are unknown-unknown. In an unknown-unknown pair, the prefix origin that has been announced the longer, we tag it as stable announcement and the other one as an unstable announcement. The graph on the negative y dimension shows the normalized count of prefix origin for these unknown-unknown pairs by visibility. Stable pairs are in green and unstable are in red. We know this heuristic is not perfect and confer that trying different threshold for announcement time difference doesn't really change the mode of the distribution. Overall, as we expect, stable prefixes dominate in terms of visibility, with most stable prefixes getting high visibility and most unstable prefixes having low visibility. More interesting are results we get when we compare both parts of the graph. Unstable prefixes reach higher levels of visibility than their RPKI invalid counterpart, both for low visibility cases and for high visibility cases. The double-pointed arrows show the distance between the low visibility and the high visibility modes. Thus, registering prefixes in the RPKI reduces the spread of invalid MOAS announcement and then helps protect legitimate prefixes from illicit announcement. Looking in more detail at high visibility prefixes, prefixes with over 60% visibility, we see that there are less than 15% of RPKI invalid MOAS prefixes compared to about 40% of unstable RPKI unknown instances. So, registering prefixes in the RPKI reduces the impact of unwanted MOAS conflict and helps protect legitimate prefixes from prefix hijack. Now, let's look at the case of SubMOAS and subprefix announcement, which can happen from other forms of hijacking. Going back to our earlier example, the difference between a MOAS conflict and a SubMOAS conflict is that in a SubMOAS, the challenging prefix is a longer one. In this case, it is a /24 instead of a /16. This is what happened in the case of a subprefix hijack. Because the announcements do not have the exact same prefix, they are not competing for one place in routing tables. Both can be there. So without the RPKI, all ASs end up with both prefixes in the routing table. And because routers use longest prefix matching to choose routes for traffic forwarding, they will attract all traffic for that subprefix. Thus, SubMOAS are highly used in hijacks to attract large portions of traffic. In a subprefix conflict, a similar thing happens since the prefix is also a longer one. And although the origin is a legitimate one, the path may be wrong, as in this example, which ends up sending the traffic the wrong way. Faking the path is known as path hijack, which is a more subtle way of hijacking than an origin hijack. To attract larger share of traffic, path hijacks usually use subprefixes. Now let's see how the RPKI can protect networks in this case. Let's say again that ASD is enforcing RPKI with its RPKI-enabled router that has access to validate ROAS, including the /16 from AS3. When the BGP message of the /24 prefix originated by AS666 arrives, it is dropped because AS666 is not the legitimate origin for the block that includes the /24 prefix. And ASD receives and checks the message originated by AS3 and then forwards it. Now, in the case of a subprefix, when the BGP's message of the /24 with AS3 in the origin and AS666 on the path arrives to D, assuming the ROA is properly configured not to accept prefixes longer than the /16, the announcement from AS666 is discarded because even if it appears to have the legitimate origin, its prefix length is longer than that authorized. Hence, the message is dropped. To check how much RPKI currently protects networks in this kind of conflict, we studied the visibility of RPKI valid prefixes for which we could see an RPKI invalid SubMOAS prefix or subprefix announcement. In both cases, we see that RPKI valid prefixes are more visible than the longer RPKI invalid SubMOAS or subprefix. When comparing the high visibility modes, we see that registering prefixes in the RPKI reduces the visibility of conflicting longer prefix in about 10 to 15% points. So RPKI registration can really benefit networks by reducing reachability of SubMOAS hijacks and from one of the most advanced hijack types, subprefix path hijacks. To conclude, here are the takeaways from our work. Our longitudinal study of RPKI enforcement show a growing number of ISPs are starting to filter RPKI invalid announcements in BGP. Our passive methods allow for continuous monitoring of RPKI enforcement and gives insights in nuances of RPKI enforcement. To the best of our knowledge, this is the first study to measure the benefit of registering prefixes in the RPKI using real data in conflicting scenarios that are what we would expect for hijacks. And we show that RPKI enforcement brings real value to networks that register the prefixes by limiting the propagation of invalid and potentially illicit announcements and effectively reducing the visibility in case of conflict that again would happen in the case of hijacks. But as you saw, RPKI filtering is not universal. More ISPs should enforce RPKI. Major networks such as AT&T, KPN, and Telia were able to do it, and we hope more networks will follow them. Thank you for watching.